Hi everybody, this video is going to go over the importance of the cell membrane, its structure, and how it helps to regulate what comes in and out of the cell. Alright, so let's go ahead and get started. In our last video, you guys were supposed to take notes on just the overall structure, and so hopefully you guys remember that hydrophilic means that it mixes with water. So if you imagine this structure going all the way around a cell, that's what's going on there. And so hydrophilic, these areas of the cell, these phosphate heads, okay, so here's a phosphate. Phosphorus atom with some oxygens, these are all going to have a negative charge here. And so if you imagine the cell, the inside of the cell is generally filled with water and the outside of the cell is surrounded by water, okay? And so if there is water around, we know that the hydrogens are going to have a partial positive charge. The oxygens have a partial negative charge. So remember, oxygen pulls electrons towards it. And so these electrons that get pulled over here are going to make this area negative, and this area remains positive. So it's going to be attracted here. Okay, now these are our lipid tails, or our fatty acid tails. These are going to be very nonpolar. It's just carbons and hydrogens, and all those bonds are evenly dispersed. So these don't mix with water very much at all. So those face each other. So we could take a blender through this whole thing and just chop it all up, and it would probably go right back to this structure because that's how everything is the most stable. Now in this picture, it kind of makes it look like these phosphate heads are just sitting here and they're fixed in this position. If you look at this animation here, you see that this is a little bit more accurate. So they tend to sort of wiggle around each other. So if you think of ducks in a bathtub, the ducks can kind of bobble up and down and kind of go around each other, and whichever way the water is flowing, they'll kind of flow with it. So it's this whole structure is quite fluid. And so when we look at a picture of this, of the cell membrane, we call this the fluid mosaic model. Okay, so it's fluid because it keeps moving. Mosaic is referring to what it looks like. If you were to take a picture of the top of the cell, it wouldn't just be phospholipids. It's going to look like a mosaic, like a tile mosaic piece of art, because all these proteins are going to be studded all over the surface. And not only are there proteins, but there are little carbohydrate chains that come off of these. These kind of help the proteins to bind to different signals that are coming from the outside of the cell. They help to mark the cell and lots of different things like that. All right, but mainly what the cell membrane is here to do is, of course, protect the inside of the cell, but also to regulate what comes in and out. So nutrients generally come in, waste goes out. All right, there's that again. Now, there's two types of movement through the cell membrane. There's what's called passive transport. Okay, and just how it sounds, this kind of happens on its own. You don't have to put a lot of effort into it. And so for the cell, anytime the cell needs to exert effort, it uses this stuff called ATP, and that's made by the mitochondria. And so passive transport, if we were to define it, passive transport is transport through the cell membrane without ATP, okay? So we'll just parentheses energy. So that's, oops, it's not letting me write over there, but that's what it is. So here are three types of passive transport, okay? The first one is just simple diffusion. Oftentimes we just say this is just simple diffusion versus facilitated diffusion. And so simple diffusion is where materials are going from high concentration and they're traveling through the membrane to low concentration. Okay, and even if there was no membrane, we would still call this simple diffusion. It just happens to be that these molecules are small enough. All right, so if we were to think about what the properties of these molecules might be, they're definitely going to be small. Excuse me. And the other thing is they must be nonpolar, because remember, this whole area is hydrophobic. So to be able to get through that, they're going to need to be nonpolar. Okay, so if they were polar, they would be way more attracted to this water, and so there's no way they could pass through. They would just kind of stay on the outside. Okay, now let's take a look at these two. So facilitated diffusion is when we have a slightly bigger type of molecule. So these things will not wiggle through the phospholipids. So that can be due to size. Okay, so it could be large size, or they could be polar. Okay, so anytime something's big enough or polar enough, it's gonna have to go through a protein. Okay, so this type of transport protein is called a carrier. So if you can imagine, this is going to open up on this side to let this molecule out. And then it can close up and let more in this way. So this carrier protein kind of bobs up and down, or kind of, kind of like scissors opening and closing to let all these things in. And notice we're still going from high concentration to low. There's nothing the cell has to do. It's just the fact that all of the water and all this stuff is just moving around. We know molecules are just constantly moving. And so if there's a lot of them on one side, they're just eventually going to make their way over here until it's equal on both sides, okay? So it's important to note that diffusion will occur until there are equal numbers of these molecules on either side. That's called equilibrium. Okay, so when we say equilibrium, that means, oops, I'll write it over here, no net movement. Okay, so what I mean by net movement is we're always going to have molecules kind of wandering in and out, but there's not going to be an overall movement in one direction, okay? Now, this guy right here, this is what we call a channel protein. Okay, so rather than open and close like a Pac-Man mouth here, this is just simply a tunnel. And so if these things are shaped the right way, exactly the right size, and the right polarity, they will be able to be attracted to the inside of this protein and find their way through. All right, so here's a picture of just simple diffusion. You see it starts at high concentration over here, and as they just naturally move, eventually they're all over the place, okay? It's kind of like keeping kindergartners in a corner of the room. It's not going to happen for long. They're just crazy. They're just going to be bouncing off the walls real soon, all right? Now, this kind of shows you how it happens in facilitated diffusion. So here are our transport protein, and everything's just going to be kind of going through from high concentration to low. All right, another type of passive transport is the transport of water through the cell membrane. And so if you remember what the cell membrane looks like, oops, okay, the cell membrane kind of looks like this on one side, right? Okay, so there's our phospholipid bilayer, and what you'll see is a little type of kind of curly small protein like that. This is what's called an aquaporin. Okay, so these are little tiny proteins that are just big enough and just polar enough, and they sit right there, and that allows water to pass through. Okay, so even though water is a polar molecule, it's able to freely pass through the cell membrane. All right, so these only let water in and out. All right, so osmosis, by definition, is osmosis. Okay, by definition, it's the movement of water through a semi-permeable membrane. All right, so anytime water is moving across a membrane, whether that be into the cell or out of the cell, it's still going to be considered osmosis. All right, now there's some terms you guys have to know. All right, so notice this arrow is actually pointing to the water here. It's not pointing to the cell. So all of these are pointing to this water. All right, let's start over here with hypertonic. Okay, hyper means more. Tonic, okay, tonic means this word, solutes. Oops, it's still not letting me write over there. All right, so hypertonic means solutes. Well, what's a solute? Okay, so let's write down some solutes. Okay, solutes are anything that can dissolve in water, all right? So that could be sugar, that could be salt, or a number of other things that could dissolve in water, okay? So hypertonic means there are a lot of solutes on the outside of this cell. And so what we see here is a normal cell. This one seems to be blown up. and this one's really shriveling up. So let's think about what's going on here. So every cell is going to have a little bit of solutes inside, okay? Not a ton, but you know, the cell contains sugars because that's what it, you know, consumes. And so there's going to be some salts for balance. So there's going to be some solutes in there. But hypertonic, that's what this is. So it's going to be super concentrated with solutes here, okay? Okay. So what ends up happening here is water is going to be going in and out of this cell constantly because there's aquaporins. But the thing is, water's attracted to solutes, okay? So always remember, water follows, geez, that's really annoying. I'm gonna have to draw it here. Let's just make sure you write down, water follows solutes. Okay, so if you can determine where most of the solutes are, and in this picture, they already tell you, most of the solutes are on the outside of the cell. And notice this big arrow right here. That means water is leaving the cell. And they're mainly leaving because, well, they're attracted to all these solutes. And so maybe a little bit's coming in, but a whole lot's going out. All right, now let's go back and look at this isotonic one. So isotonic means that the liquid here is actually equal to that of the cell. So there's solutes in here, and there's probably an equal concentration out here. Okay, so not much more or less. So you can see that the water in and the water out are equal. So there's not one area attracting more water than the other. All right, so let's take a look at this. So now our water here is hypotonic, okay? So let's take an extreme example of that. Let's say this is fresh water, okay? You really can't put blood in fresh water because what's going to end up happening is there's some solutes on the inside, and like we said, water follows solutes. So big arrow in, water is going to come in here, attract to these solutes, and what will eventually happen is this cell will burst, okay? We call that lysis, okay? And so this will burst and die. So usually our blood plasma has a certain level, a certain molarity of salts, okay, to kind of keep an osmotic balance. All right, now the water out here is hypotonic, but what that means is that in this case, the cell is also hypertonic. Okay, so over here, this time, the liquid on the outside is hypertonic. The inside of the cell is hypo. Okay, so hyper and hypotonic are relative terms, and you always want to make sure you indicate where it is you're talking about. So here they give you an arrow. If you're just writing, you want to just say, this cell is hypertonic, or the solution on the outside is hypertonic. So just make sure you specify, okay? All right, so let's look at some animations real quick. I'm going to keep those. All right. Now, I'm going to refresh this real quick. How do I do that? Sorry, I don't usually use this one. Let's go back. Here we go. All right, so here is a semi-permeable membrane. Here's the waters going back and forth. You see that there's no solutes, but let's go ahead and add salt and see how that affects things. So you see that once the water molecules attach here, they're kind of stuck, and you see that this water level goes up as a result because these guys are not going to get out of there. So this sodium and chloride, they are charged. They're not going to be able to go across. So solutes generally stay where they are, but water can go back and forth, okay? And so it's going to go until it reaches equilibrium. If you actually count these water molecules and you count the free ones, not the ones attached here, just the free ones, they are about equal, okay? So that's how in osmosis we reach equilibrium. So equilibrium really means whatever's not attached to the solutes. All right, let's see here. Let's go ahead and move on. Actually, we'll save active transport for the next video. So just close this up and open that one up. All right, thank you.